There is no doubt that Dr. Kunihiko Fukushima totally deserves the 2020 Bauer Award due to his enormous contributions to artificial neural networks and deep learning. In the 1970s, he created the now popular deep convolutional neural network architecture, the CNN architecture as it is often called now, which consists of alternating convolution layers and downsampling layers, convolutional layers and so on, and he called it the neo-cognitron. It was first published in 1979 in Japanese and then in English in 1980. And here you see a modern variant of this architecture from one of our own later papers. Kunihiko Fukushima's deep neural network was inspired by Hubel and Wiesel's neurophysiological studies. Back then, biological neural networks were still an inspiration to artificial neural networks. This is not any longer the case. For decades, the field of deep neural nets has been driven by engineering and by simple mathematics without much regard for biological plausibility. Deep learning, of course, started in 1965 in the Soviet Union, more precisely in the Ukraine, with Ivagnenko and Lapa, who had the first deep learning multi-layer perceptrons that really worked with many layers. And they also did not care for neuroscience, they were mathematicians. In the early 1970s, Ivagnenko already had deep learning nets with 8 layers, something that would be called deep even in the new millennium. Kunihiko Fukushima's neo-cognitron was introduced at the end of the 1970s, which were a special decade for deep learning. And it is playing a very prominent role in this history of deep learning. Today, everybody is using variants of this CNN architecture for computer vision and other applications. How does it work? The typically rectangular receptive field of a neural unit, a neuron with a given weight vector, a so-called filter, is shifted step by step across a two-dimensional array of input values such as the pixels of an image. Usually there are several such filters, and the resulting array of subsequent activations of this unit can then provide inputs to higher level units and so on. Due to massive weight replication, relatively few parameters may be necessary to describe the behavior of such a convolutional layer, which typically feeds a so-called downsampling layer consisting of units whose fixed weight connections originate from physical neighbors in the convolutional layer below. And Kunihiko Fukushima's downsampling units use something called spatial averaging to become active if at least one of their inputs is active. And their responses are insensitive to certain small image shifts. Now, interestingly, the backpropagation algorithm was already well known when Kunihiko Fukushima did his work in the late 1970s, but he did not use backpropagation to train his convolutional architecture. Instead, he used unsupervised learning rules. Today, however, his architecture is indeed trained by modern backpropagation, which was published in 1970 by Seppo Linna in Finland, and first applied to neural networks by Paul Werbers in 1982, extending thoughts in his 1974 thesis. And backpropagation is also known as the reverse mode of automatic differentiation. In 1987, neural nets with convolutions were combined by Alex Weibel with backpropagation and with weight sharing. Alex Weibel neither called this neocognitrons nor CNNs, but he called it TDNNs. He successfully applied them to speech recognition. Interestingly, Alex Weibel did this work also in Japan, like Fukushima, but he was working in a different lab. I was wondering, why is it that the basic concepts of modern deep CNNs emerged in Japan, of all places, between 1979 and 1987? Let's look back at the 1980s. Back then, Japan was the envy of the world. Among the large nations, it was the richest per capita. I was a young man back then, and I remember that 8 of the top 10 banks in the world were Japanese. And the Tokyo stock market was the world's largest, and the central square mile of Tokyo, had the value of California. And before the big crash, at the end of the 1980s, Japan was growing so quickly that many predicted that by 2005 it would have the world's biggest economy, despite having only 120 million people or so. Also, Japan soon had far more robots than any other nation. In fact, at some point, half of the robots of the world were based in Japan. And they also had by far the most expensive computer science and artificial intelligence project back then. It was called the 5th Generation Project. And science fiction authors such as William Gibson, who coined the notion of cyberspace in the 1980s before the World Wide Web was created in Switzerland, here where I'm talking to you, such science fiction authors looked to Japan for inspiration. So this was the environment where both Kunihiko Fukushima and Alex Weibel did their work. Alex Weibel was an immigrant from Europe, and they worked there on what is now called CNNs. Interestingly, the Japanese 5th Generation AI project was not at all about neural networks. It was about logic programming, mostly, essentially in the style of Kurt Gödel, the Austrian mathematician who in 1931 founded theoretical computer science by showing the limitations of theorem proving and computing in general. So Fukushima and Weibel were kind of outsiders back then, but at least there was sufficient funding in Japan for this type of research, and today the rest of the world can be thankful for that. Since 1989, the team of a French researcher named Yann LeCun has made additional important contributions to CNNs, especially for two-dimensional images. In 1993, Yuan Wang replaced Fukushima's spatial averaging by something that is called max pooling, which is widely used today. With max pooling, a two-dimensional layer or array of unit activations is partitioned into smaller rectangular arrays, and each is replaced in a downsampling layer by the activation of its maximally active unit. So that's called max pooling, widely used today. My own labs in Germany and in Switzerland had nothing to do with the origins of CNNs. Instead, in the 1980s and 90s, we focused on the most powerful type of neural nets, on the recurrent neural nets, to process sequential data. Think of text and speech and videos. And this has become successful business. We called our LSTM arguably the most commercial AI achievement. Recently, I learned that by the end of the 2010s, our 1997 LSTM paper, first author, my brilliant student, Sepp Hochreiter, got more citations per year than any other computer science paper of the 20th century. And in fact, since 2015, LSTM, trained by our CTC of 2006, first author Alex Graves, has done Google's greatly improved speech recognition on billions of smartphones, and our LSTM also was the core of the greatly improved Google Translate in 2016. In fact, by 2016, over a quarter of the awesome computational power for inference in all those Google data centers was used for LSTM. And Facebook announced in 2017 that they are using LSTM to translate 30 billion messages per week, or over 50,000 per second. Compare, the most popular YouTube video needed 2 years to achieve only 6 billion clicks. LSTM also learned to improve Microsoft software and Apple Siri and QuickType on billions of iPhones, and to create the answers for Amazon, Alexa, and the great companies from Asia, Samsung, Alibaba, Tencent, Huawei, and so on, are also using it a lot for automatic translation and so on. Since the end of the 2010s, however, a lot of natural language processing is done by transformers. For long input sequences, the efficiency was improved through linear transformers, whose core is actually formally equivalent to the fast-weight programmers that I published in 1991. 30 years ago. How do those fast-weight programmers work? A feed-forward network slowly learns by gradient descent to manipulate, to compute weight changes of a fast-weight network, and it computes fast weight changes through additive outer products of self-invented activation patterns. And today, often, this is now called keys and values for self-attention, terminology that I introduced in 1993. So that was the work we did, which was not at all about CNNs. In the 2000s, however, my team was also able to contribute something to neocognitron-like CNNs, as introduced by Kunihiko Fukushima. In 2010, we first showed that unsupervised pre-training, something that I introduced in 1991 for deep learning, that unsupervised pre-training is not necessary to train deep neural nets with many layers, contrary to claims by a well-known researcher who said that nobody in their right mind would ever suggest this. And one reviewer called this a wake-up call to the machine learning community. And here we profited a lot from the exponential fall of computing costs. Since 1941, when Konrad Zuse built the first working program-controlled general-purpose computer, every 5 years, compute got 10 times cheaper. Zuse's machine could do about 1 elementary operation per second. Today, 80 years after Zuse, compute has become 10 million billion times cheaper. And so in 2011 came our deep and fast CNN, neocognitron like CNN, called the DANet, named after my outstanding Romanian postdoc Dan Claudiu Girijan, also known as Dan Girijan. In 2021 we are celebrating its 10-year anniversary. So it's a very nice coincidence that here in 2021 I can talk about Kunihiko Fukushima's pioneering work in the context of this accelerated version of what he did back then. And DANet was the first pure deep convolutional neural network to win computer vision contests in 2011. For a while, DANet enjoyed a monopoly. From 2011 to 2012, it won every single computer vision contest it entered, winning 4 of them in a row, driven by a very fast implementation based on graphics processing units, GPUs. Since 2011, DANet has attracted tremendous interest from industry. Its temporary monopoly on winning computer vision competitions made it the first deep CNN to win a Chinese handwriting recognition competition in May 2011, a traffic sign recognition contest in August 2011, and the first image segmentation contest in May 2012, and a contest on object detection in large images in September 2012. And the latter was actually a medical imaging contest on cancer detection. That was the first time that a CNN won a medical imaging contest also. And our CNN-based image scanners were 1,000 times faster than previous methods. The significance of these kind of improvements for the healthcare sector is obvious. Today, IBM, Siemens, Google, everybody, many startups are pursuing this approach. Remarkably, already in 2011, DANet achieved the first superhuman performance in a vision challenge in 2011, although compute was still 100 times more expensive than today. DANet was 3 times better than the runner-up, which was the net by Dr. LeCun's team. In July 2012, our CVPR paper on DANet hit the computer vision community, and the similar AlexNet, citing DANet, joined the CNN party in December 2012. Our even much deeper HighwayNet of May 2015 and its special case ResNet, the residual net, of December 2015 further improved the performance. HighwayNets have hundreds of layers, not just tens of layers, but really hundreds of layers. And a ResNet is a HighwayNet whose gates are always open. Today, a decade after the DANet, everybody is using fast, deep CNNs with the architecture of Kunihiko Fukushima for computer vision. In sum, the now widely used convolutional neural network architecture is an essential ingredient of deep learning, and it's essentially the baby of Kunihiko Fukushima. I am personally greatly indebted to his work. Finally, I should mention something. The nominators of Kunihiko Fukushima asked me for a support letter. I told them that I might have a conflict of interest because I was told that I'll get nominated for this award myself. The nominators did not mind though. And so I was happy to write a glowing letter for Kunihiko, because it's clear that Kunihiko Fukushima totally deserves this award. Congrats and many thanks again to Kunihiko Fukushima. We are all looking up to him.